In the name of Allah, thank you so much and welcome back to the lecture number 6, which is the starting lecture of the class number 3, which is the basic analysis. So far, we have covered the class number 1, which was about the remote sensing principles or principle of remote sensing. We covered three different chapters. It was the electromagnetic radiation, the Earth observation platforms. We covered the Earth observation instruments. In the second glance, which was about the remote sensing products, we have covered the remotely sensed data in the data formats and visualization. Now, this is the third glance. We have only one more. And the third glance is discussing about the basic analysis. And the fourth glance is discussing advanced analysis and application. So in this glance, we are having the first chapter, which is technically becoming a sixth chapter of the whole intelligence sensing and remote sensing. As we said, it will be 9. So the sixth lecture is data correction in basic tools. So this lecture is really important and it is divided into the two parts, which is about the data corrections in the basic tools. So initially we'll be discussing some of the data corrections and methods, which kind of corrections we are doing, and then basic analysis. In Now we are slowly moving towards the intelligence sensing part. We so far covered the remote sensing almost. Now we are having the data. It is acquisition has been already happened. Now we are playing with the data and preparing the data for the artificial intelligence or machine learning procedures, classifications like this stuff. So after certain types of data correction, still it is considered like as a feature engineering uh, for the basic imaging analysis, which is further prepared for the or pre-processed for the actual image analysis or the classifications or data sets or data sets which we are performing. So this is all about preparing the data for the further processing. From the data correction perspective, we have that the every remotely sensed images or data sets are normally needs an operation before it becomes effectively usable. So if the objective is that using by the data levels we have seen so far, if the objective is simple or the purpose is the simple visualization, till that stage it's enough. But if you want the purpose is to do more further analysis or prepare the data for the classification, machine learning, artificial intelligence, then we need more data corrections. So the most two important parts are the radiometric corrections, which is mostly discussing the corrects of the pixel values, and the geometric corrections. It is discussing the corrects the physical pixel location. But between both of them, we have one of the important one that is exactly the atmospheric effect we need to take into account. As we know that when we are having the reflected signal, which is bounced back from the target, when we capture them or sense them on the sensor, on the satellite, that is exactly the radiometric corrections we are doing. But in the model we are having from the target and the sensor, the atmospheric correction, then we are doing the geometric correction, which is about most the spatial information, and it is correcting the pixel location, which is located on the Earth surface or the target. So this is the main two data correction, but intermediate one is atmospheric correction we need to take into account. But that is more relevant to the radiometric, or it is can be considered as a part of the radiometric correction, and because the signal or electromagnetic wave is passing from the from the atmosphere to the destination, which is the sensor automatically. So they are affecting by the mostly atmospheric effect. And after that, we are looking into the radiometric correction by itself. So some correction step may be skipped if the final purpose is only simple visualization. We already discussed this. But for analysis or classifications, change detections, the artificial intelligence correction is usually necessary step. Start with the first one, radiometric correction, also called the radiometric calibration, is used to estimate the target reflected reflectance from the measured incoming radiation. We already know about this. This is what we are looking for. But now we are reversing these steps a little bit in the main steps which we are having in the radiometrics. So we discussed the radiometrics and quantization in the third lecture, um, in the fourth lecture of the day, remotely sensed data. We have seen the radiometrics, radiometrics and the quantization procedure, how the continuous signals are converted into the digital numbers and stored in the digital systems, the procedure of changing of the continuous signals into discrete values is exactly the quantization procedure. So here we are having the digital numbers. We are going to the back procedure. We are unfolding the procedure now. The digital numbers and the sensor radiance conversion at the sensor radiance to the surface radiance from the solar into tomography correction. Then we are having the reflectance estimation. We discussed already this that the ultimate objective is that we need to achieve the reflectance, which can reveal the characteristic or the properties of the object and the target on the line surface. And we are mostly interested in this, and what we are capturing, that is exactly the radiance or intensity of the electromagnetic wave. So satellite sensor first record the digital values, but we usually want a physically meaningful reflectance value. It is not about we only capture these digital value, but mostly interested in the reflectance values for what we are looking for ultimately. So this is exactly what we call the radiometric correction. As I said, that the atmospheric factor or the atmospheric correction is an intermediate part from the land surface to from the land surface or the target to the sensor. In the middle we have atmosphere. So in the ideal case, all incoming radiation measured by the sensor would come only from the target reflection. It's obvious, but in reality, radiation is affected by multiple things. It's atmospheric scattering. We discussed the types of the scattering in the first lecture, relay scattering, scattering, and Mie scattering. The atmospheric scattering is one of the reason that is in the atmospheric uh, corrections we are doing, and the another one is atmospheric absorption. So there are multiple things that they can absorb, like gases, molecules, and the aerosols, water, vapors, and many things in clouds. Path radiance and the path transmission. We discussed the radiance, absorption, scattering, all this. With the low absorption and low scattering, we say this is the better transmissions. So illumination condition is also important. How much is the light or the solar radiance is available, and topography, the landforms, how it looks. So all these really important things are matters while we are also taking into account the radiometric correction, because before radiometric corrections, uh, we can assume that initially we are doing the radiometric correction, then we are doing the atmospheric correction. After that, we are doing the third one, which is the geometric correction, which is more relevant to the spatial correction. Atmospheric correction tries to remove the atmospheric effects so that the image better represents the Earth surfaces. This is the overall goal, and it is more relevant to in the which is happening in the middle, because the reflected signals is going to be sensed by the sensor. So in the middle, we are facing the atmospheric effect. So initially, we are performing on the observed data the radiometric correction. Then, after performing the radiometric correction, we are looking into the atmospheric correction. Then we are looking into the geometric correction. Here is the processing chain, digital number to reflectance. Again, we already seen this. The digital number at sensor radiance we are having, then the at surface radiance, then we are having at surface reflectance. This is overall they are discussing how it looks in how we are unfolding back then in the lectures is giving a general processing chain. Each step requires additional information such as the calibration coefficient, atmospheric models, path, uh, path transmittance, and we have seen the uh, exo, exo, exotomospheric solar radiance, and we have seen the solar path transmission. in diffuse radiance, which is the type, the error matter reflection, digital elevation model or DM. So we already seen this. This is the unfolding process, or you can say the processing chain from the digital number to the reflectance. So all of these steps are required as additional information, either if it is a calibration or it is atmospheric models, the path transmittance and the path radiance in the exalt mass for aspheric solar radiance, and either it is a solar path transmittance and the diffuse radiance. All of these are required additional information to avoid the atmospheric effect, and at the same time also the objective is to have the correct reflectance really which can represent these line surfaces. We have the visual effects of radiometric correction. Like, let's suppose we perform the initial step on the radiometric correction of a certain captured signal. What effect they have? So first of all, if you see to the right side picture, maybe it's not more visible, but somehow the right one side is the level 1 to A, level 1 to A, and the left one is level 1C. The level 1C has the top atmospheric correction, but not the bottom atmospheric correction. But level 1 2 has the bottom atmospheric correction. It looks more visible. And this is why we are discussing from the perspective of the data levels of the ESA of European Space Agency. At the level 1 2, the Sentinel-2 level 1C and level 1 2 imagery is representing two different data levels. The level 1C is the top atmospheric reflectance, and the level 2A is the bottom atmospheric reflectance, but after the atmospheric corrections. So when we are correcting the atmospheric correction, so it is exactly revealing the more visible visibility of the land surface on the objects. So the visual difference appears because the level 2A has atmospheric correction applied. Now the third one comes into the picture, which is geometric correction, which is really important, which is more relevant to the spatial information. This is the one, geometric correction. So geometric corrections corrects the spatial distortion we are having in the neighborhoods of the spatial distortion. So the geometric correction is mostly around working with that, assign map-like properties to an images. So the give a look more like map-like properties to an image or a data set. Satellite images may be geometrically distorted because of the acquisition geometry, as we discussed in the second lecture of the Earth observation of Earth observation platforms. So in the geometry of the radar, we have seen how they are taking the acquisitions of nadir and nadir, as if it is nadiral or it is off nadiral. So this acquisition geometry really matters, the perspective of the view versus vertical projection. And exactly the same again, the acquisition geometry they are discussing, it is a vertical, like it's taken on the central point of the nadir. Earth shape and rotation, this really matters on which part of the earth we are, if it is like the slope part or either it is the rotation really matters. So the atmospheric effects, even, yeah, we have seen the two effects should be already, or the two correction has been already be performed. So atmospheric effect is also affecting the geometric correction. Inherent relief is another one, a uh, major distortion reason. Uncorrected datasets may not match maps or other datasets correctly. So that's why we need geometric corrections, and it wraps the images so that it conforms to acquire a map projection and exact coordinate system. This is due to the geometric resolution or geometric information, which is exactly the spatial information about the map like images or data sets we are seeing. why geometric correction matters? Like, we have seen two types of the correction. The one was the radiometric, and we discussed the reasons in the middle when there was atmospheric factor. So, like, what happens with the geometric corrections? Actually, after geometric corrections, the user can click a point on the image and find its true coordinates. So this is the effect we discussed in the previous slide, that the geometric correction wraps the image so that it conforms to required map. Projection in coordinate system. The coordinate system is really helping us that the whenever we are clicking on any point of the image, so we can get coordinates or either input field coordinates and located on the image. So overlay satellite data with maps, GIS layers, or other satellite scenes. So this is exactly they are helping us with the GIS layers and the overlays of the satellite data with maps. So for the precise geometric correction, digital elevation model or DM models are often needed. Still obvious that is needed for the exact geometric corrections. We are needing DMs is often required. Now what's happening? So far we have seen the data corrections. So corrected data after radiometric and geometric correction, atmospheric correction, remote lessons data can be passed to later processing step. As I said in the start of this lecture, this is more step of like a feature engineering for the further processing. The next step is usually uses the basic tools to prepare the data for better information extraction. After doing these data corrections in the later processing is make the data for more advanced analysis, which is most probably the basic tools of the image analysis. Now we're starting the second part of this lecture, which is about the basic tools. So basic tools are image processing operations in after pre-processing. Their goal is not usually to produce the final answer directly. If we see the first line, the basic tools are images processing operation. That is obvious. Like, what do you mean by the basic? It is the almost the image processing operation used after pre-processing. After pre-processing stage is the data correction. Now the data is pre-processed. We are processing the data more for the further analysis or further advanced analysis. So the goal is not usually to produce the final answer directly, but the goal is to make the data more suitable for later analysis. So they help to reduce the noise. Basic tools are helping us to reduce the noise, remove the redundant information or duplicated information, highlights useful patterns, and prepare the data for clarification, classification, or artificial intelligence models. The main objective of this basic analysis to prepare the data for the classification and artificial intelligence models. Support feature extraction. This is also really important aspect of the basic analysis that they should have to support the feature extraction. So basic tools acts like a feature engineering in the Earth observation data. We already discussed in the start of the lecture that this basic tool or this pre data is helping us to feature engineering for the Earth observation data. Why basic tools are needed for artificial intelligence? Like why we are performing such basic analysis or basic tools for the further analysis of the data or the perspective of the artificial intelligence. So feeding raw satellites data directly into artificial intelligence model does not usually work well because of the too much noise, so too many variability factors and redundant information. And this is the why we are using to remove the noise, variability factor, and redundant information and hidden patterns not obvious in the raw pixels. So, I mean, in the raw pixels, it is really difficult to identify the hidden patterns by the artificial intelligence due to the high variability. So basic mathematically manipulate, filter, and clean pixels so that the useful patterns becomes easier for machine learning or artificial intelligence algorithm to detect. The idea is mainly here we are minimizing the computation power of the artificial intelligence for using of the basic tools like is the basic filtering, cleaning, so the useful pattern can be easily detected by machine learning algorithms. So this is the main chapter or slide of this whole lecture. So on we will be following almost the examples of the categories of the basic tools. So we are categorizing initially, and then what is the work and its examples. In each example will be taken into the account for the further clarification and discussion. So the first one category, it is called point operation. Point operation is an individual pixels or corresponding pixels. So this is exactly the idea of the point operation. We are having the image sum, difference, ratio, thresholding, division, multiplication. So these are the basic examples we will be taking into account. So the point operation is working only on a single pixels or individual pixel or its corresponding. Local operation. Local operation is exactly working around the pixel neighborhood. What is in the pixel neighborhood? So we are here working on the filtering, convolution. Here, this convolution is directly bridging with the CNN, convolutional neural network. We will discuss this more in detail. Then we have morphological or object level operations. This is we already seen of some of the example of the pixel versus image based analysis in the previous some of the chapters. But again, here it is repeating. We will see more from the perspective of the data correction and its basic tools analysis. So the work is on the shape or the object structure. And examples are dilation or erosions or segmentation. In the last one category, which is the global operation, which is the last operation category of the basic tools, it is the idea that they are doing the whole image or data set. So now we are applying on a whole data set the analysis. So for we were starting from the pixel, the neighborhood, we are being on the shape or object. Now we are not leaving the objects, pixels, neighbors, and applying on the whole data sets. So it's called like some of the operations are common principal component analysis, histogramic equalization, and support vector machines. So these are some of the examples of the categories of basic tools. So we are starting from the base category of point operations, which is exactly this image sum. From the point operation, image math. What is image math? We're starting with the mathematical operations. As I say to you, this is the summation operation. So the formula is Zij in the subscript equals to Xij times Yij. So this is the point operation, apply mathematical operation pixel by pixel. So this is the basic operation include like subtraction, summation, multiplication, division. Important assumption here is the input image must be co-located. From the co-located means that the corresponding pixel must refer to the same geographical location. It should not be the different geographical location, otherwise it can coincide. So the what is ij in the xij and yij are the corresponding pixels from two data sets, but from the same geographical locations. We are starting with the image sum. For the image sum, the similar images for such as the multi-temporal sequence. We discussed the multi-temporal means that the data has been taken in multiple times in multiple layers. So the results may behave like averaging after renormalization. So we are normalizing and again renormalizing the data by applying this summation. So what is the main effects? It reduces the noise, creates smoother data, and useful, especially when several similar images are averaged. When there are similar images are already averaging, then we are again performing the image summation. That's why we call them renormalization. And the formula is given f of r x equals to f of 1 xy plus 1 plus f of 2 xy. So the summation becomes it's a two different data set values from the same geographical location. And it's mainly helping to averaging after renormalization. Exactly. In the last we have discussed that is useful, especially when several similar images are averaged. We are having the image differentiation or differencing in change deduction. The idea of the differencing or subtracting is the change reduction. As I already said in the start of the lecture, in the radiometric, uh, I think so. This math operation will help us to identify the change. So if the IFF xy equals to f1 xy minus f of 2 xy. So image differencing is widely used for the change detection because we are differentiating the one from the other data. So the examples are the flood mapping, pre-event or post-event comparison, urban expansion, and vegetation. This is the simple, we can say the some of the effects you would like to identify in the burn area detection. So the resulting images can be converted into the change map by applying threshold. So here we are getting exactly the change map by just applying a threshold. Values near zero means little or no change, or the values from zero indicate significant change. Far from zero mean closer to one, they are having some significant changes. So this is how we are representing the change in no change and significant change. So this is the overall idea of how we are differentiating and what is the benefit. Thresholding. Thresholding compares each pixel values with the predefined threshold. So we are comparing a predefined threshold with each pixel. So basic idea, if a pixel value is below the threshold, it is mean class is zero, or if the pixel value is above the threshold, its class is one. As we have seen in the previous the image differencing that the values far from the zero indicate significant change. If there is a value near to zero, it means no change. The same is here. Its value is above the threshold means it is one. It is often used to create the mask. Okay, the idea of the thresholding is actually mask, which can be later on helping in the multiplication. Examples, which vegetation masks from NDVI, normalized difference vegetation index, and device stands for this, like water mask, flood mask, and the cloud mask. So these masks are helping us the multiple analysis. The lecture also mentioned also criterion. So the also criterion is exactly one of the thresholding concepts for using for the masking, which automatically determines an optimal global thresholds. And we will see some of the global operations or categories of the uh, basic tools. So this is the optimal global threshold when there are two classes with the Gaussian-like distribution. So we are not going more in detail. This is a separate criterion for the thresholds, but we generally understand about what is thresholding. It is basically the mask, image multiplication in mask. Now this mask comes into the picture here. Image multiplication in masks are helping with this operation of the image multiplication. Image multiplication is often used as with a binary mask 0, 1. Value 0, 1 keeps the pixel If the value 1 is, it means we are keeping the pixel. It is important because it is really making a significant difference. Value 0, remove the pixel. The main purpose to mask out irrelevant part of an image. So let's suppose we are having an image or a data set and we would like to remove irrelevant data from that. So there we are using a mask with the multiplication. So example is applying a mask, a cloud mask to land set data. So we are having a land set data and we would like to remove the mask of the cloud. So we are making the thresholding, and based on the thresholding idea, then it's a complete mask. Then we are multiplying the land set data with the mask and we will have the uh, free data land set data of clouds. This is the objective. And all these operations are point operations. So for image divisions in band ratios, so like if we divide the B8 to divide by B4, B4 is a red band and B8 is a near infrared. So this is exactly helping in identifying the vegetations. Uh, Image division is widely used in the remote sensing. This is one of the mostly used in the wide remote sensing. Why it is useful? Some reflectance features are clearer in the band ratios. Like we discussed the near infrared red band channel. So illumination effects can be reduced. Retrieval spectral reference become more visible. Example, this ratio is useful because vegetation reflects strongly in near infrared and absorb the more infrared. So they are absorbing the red in the near infrared, the vegetation reflects very strongly. So this is the image division in the band ratio. Filtering. So filtering is the now second local operations and it's applying to neighborhood pixels. So it starts with the Gij equals to Hij times Fij, and this filtering performs operations on a local neighborhood around a pixels. Linear filtering is usually defined by the convolution. So here in the above formula, the f of ij is the original image and hij is the filter kernel. So the filter kernel is already predefined to what to do with the picture, and gij is the filtered image. After multiplications of the kernel with the original image, so the kernel is basically determining what the filter does or what the filter do. So this is what filter. We have seen here that this linear filtering is usually defined by the convolution. We will later on bridging this to the CNN. Now we are having low pass and high pass filters. These are the further types of the filters. So low pass filters are using for smoothing the image overall, and it replaces pixels with an average for its neighborhood. Let's suppose if we are having a neighborhood value is very higher, so using the replacing the pixels with an average neighborhood, so it's mainly used for the noise reductions and removing unrepresented pixel values. Like if we give an example of in for the intuitions, like an out the data set, so we are removing that outlier to become a representative average of the data. So this is exactly the low pass filter doing. In high pass filter is filtering enhance. So high pass filtering enhance the difference in ages, and it is mainly used for the age enhancement in the gradient detections in the boundary reductions. So low pass is equals to smoothing, but high pass is equal for the age or the details enhancement, specific details enhancement. As I said to you in the filtering, the convolution is now connecting to the neural networks, that the linear filtering is exactly the linear filtering of the kernel we are using. So it is usually defined by the convolution. So here we are bridging to convolutional neural network or CNNs. Filters are building blocks of the convolutional neural networks. Obvious is classical information, the traditional image processing means the filter kernels are manually designed by like example of Sobel or edge filters, Gaussians. So what the convolution neural network do, use the same convolution operations of the kernel, automatically learn optimal kernel weights from the data during the training. So they are automatically estimating the kernel procedure and optimal kernel weights from the data during the training. In early CNN layers behave like a learned age. They are learned about the age or texture filters, while the deeper layers of the combine the simple patterns into the complex objects and scenes. This is how the convolutional networks operates based on the filters and how the filters are helping the convolutional neural networks to learn and the first layer about the texture information in the edges of the pictures. Now we are discussing the non-linear filtering. So far it is the cases of the linear filtering case. In the non-linear filtering, do not use the simple linear convolutions now anymore. So major classes are included if we take into account like feature extraction, age extractors such as Sobel and Roberts. So if we are interested in the ages extraction based on these methods, morphological operations, and we would like to in the special information, if you are interested in the morphological operations, so it's all the non-linear filtering cases and the texture filtering, and it's also coming under the special information adaptive filters. So they should have to adopt themselves. So in the non-linear filters, we are not anymore the linear convolution, but these are the major classes included, like the feature instructs extractions and the edge extractors, morphological operation, texture, and adaptive filters. We are starting with the couple of them from this nonlinear filtering, the feature extraction or the feature detection. Feature detection identifies meaningful image feature based on the distinguish and distribution of the pixels gray level. Like the feature detection in the picture is mainly by the distribution of the pixels of the grayscale. From that numbers, we are basically identifying the feature detection. Example, line detection, circle detection, template matching, or age detection. These are the sample examples of how the feature detections work based on the distributions of the pixels of the grayscales or gray level. Another one example of the nonlinearity is the age detection is identifies the discontinuities in raster values in Earth observation. So this is one of the important concept. In the age detections identification identifies the discontinuities in the raster values. We already know about the remote sensing using the raster grid information or data format. So in the age detection, identify the discontinuities in the raster value. So we can identify that discontinuities, it is detected as the age. So in the Earth observation, ages may represent the changes of the land cover type. Okay, that there is a change in the land cover type, the change of the land cover properties in the boundary between the homogeneous data or the homogeneous area. So how we should differentiate them in the homogeneous area, this boundary between the roads, building, rivers, and the urban structure. Age detection is really important in real application of the administrative boundaries. A special type of the example of the age detector, it is a canny age detector. The canny age detector is one of the most popular age detection method, and it is steps are the below. They are reducing the noise by using the Gaussian filtering, then computing of the image intensity gradient in non-maximum separations, also called thinning. So after that, they are applying high stresses thresholding. So the canine edges detection is useful because it reduces the noise and reduce thin and produce a thin, meaningful images. So this is a little bit the good version of the edge detection from the classical. So it is basically reducing the noise and also produce the thin, meaningful edges. Now we are coming into the third basic category of the basic tools for the basic analysis. So that is morphological operations. In the morphological operations, we are having two main operations. If we go back to the previous main slide, which where we have started all of the operations, we have seen the point-wise local operation, which was the pixel neighborhood. Now we are discussing the morphological or the object level operation. Now we are slowly increasing the levels of the operation. Initially, it was in the pixel, the neighborhood. Now it is in the object or the shape. So in that case, we are having the main two operations: dilation and erosions or in segmentation. This is exactly the two operations we are having here in the erosions and dilutions. Dilation, these are the main operations in the image analysis or image processing. So erosion is using the minimum operations, but on the other hand, dilation using maximum operation. What they are doing, in the minimum operations of the erosions shrinks the bright or the foreground regions, not the background, the foreground regions. So they are trying to shrink the bright or the foreground region. In the dilation, they are using the opposite, the maximum operations, which can expand the bright or the foreground regions. So this is working in opposite way. One of them is shrinks the white or the foreground regions. On the other hand, the dilation is using the maximum operations to expand the bright or foreground regions. So it is a trade-off we are maintaining where we are required the erosion, where we are required the dilation in the morphological operations. They are useful for cleaning masks. The mask we have discussed for the multiplication to help us uh, in removing like cloud masks and many more. So they are cleaning more the masks in filling the gaps, removing the noise, in modifying the object boundary. Exactly, these are the some of the benefits on the object level of the morphological operations. If you see that they are also useful for cleaning the mask, means we already designed the mask in use by the multiplication. So in this case, the erosion in dilation is mainly looking the overall picture of the object, what is applied already. So that's why they are not exactly cleaning the mask which we designed or the kernel we have seen so far. But the after perform the on a certain area of the images, now we are discussing that was only for the neighborhood, but this is only for the overall object. We are discussing a data set. It is a little bit higher level of the basic analysis operations. And then they are filling the gaps of theirs. Like for the filling of the gaps, what we will do, we are using the dilation because that's using the maximum operation. It's explained the bright or the foreground regions. And for removing noise, we are using the erosions. So we are shrinking the bright or the foreground regions and modifying the object boundaries accordingly. Image segmentation is the another example of the morphological operations of the basic image analysis. The segmentation means partitioning an image into the connected or the homogeneous areas. The segments may be called superpixels or specified pixels. Segmentation is useful because it isolates the objects. So we are taking the objects from the complete data sets or the images in the segmentations based on the superpixels and the group similar pixels. We are grouping the similar pixels required in a certain part. enlarge the statistical basis and prepare the data for the object-based analysis. So this is the help of the segmentations from the morphological operations for the object-based analysis. Now we are discussing the geographic object-based based analysis. We have already seen the pixel-based versus the image for the object-based analysis, the previous chapters, and where we have already seen the GBIA, which is stands for the geographic-based geographic object-based image analysis. So it is a pixel-based analysis is useful when the spatial information is limited. So we are saying the pixel-based analysis is important in case when we are having a limited spatial information, such as with the coarse spatial resolution. Coarse spatial resolution means the lower spatial resolution, but with the higher spatial resolution data, attention shifts automatically from the spectral information to the spatial information. As we have seen, that's why in the coarse or the lower spatial resolution case, the pixel-based analysis is useful, where the spatial information is limited or the spatial resolution is limited. But when the spatial resolution is higher, so then attention automatically shifts from the spectrum to the spatial information. So this creates a shift. The pixel-based analysis are the superpixels using for erosion, dilation, segmentation, and also can be used for the object-based analysis. But the geographic object-based image analysis are meaningful image objects rather than the individual pixel. So they are not only working on individual pictures, but along the whole image objects. This is the main differences of GeoBIA, the geographic object-based image analysis, and the pixel-based analysis. Segments versus image objects. We have seen the segments is the partitioning of the data set based on the superpixel, based on the data features how much features data they have for the pictures and what we would like to extract or partition. Then image-based are meaningful grouping created for a specific context or aim. So the image-based object is very meaningful grouping created for a specific context or so the segment is actually partitioning of the data sets on the data features. But the image segment is data-driven partitioning in the image object is meaningful object for an application. This is exactly the image object is for a complete set of application. On the other hand, the segment is the only data-driven partitioning on a data set. So this is what segments versus image objects. Image objects is exactly like meaningful objects for an application, for a complete set of application. So data or the segment is one step for the complete image objects to become more meaningful application. The last one operation, which is the global operation, the basic analysis. The global operations considers the whole image at once. It is more next level from the shape or the object in this whole picture. It is the whole picture now we are working around. The transformation of a one pixel depends on the statistical properties of the entire data set. The main purpose is the transmission of a one pixel depends on the statistical properties of the entire data set. So this is really important information. Like when we are transforming one pixel, so it depends upon the statistical properties of the entire data set. So here the every pixels, tiny pixels of the whole image can be changed or transformed. Main features are the reduced redundancy as the whole object of the basic analysis again, the fight curse of dimensionality, standardize the data scales, scaling the data in simple terms, concentrate information. We are looking for more concentrate information, transfer the physical bands into the informational components. Uh, we are working with the bands to transform them into more informational components. So some of the examples of the global components, as I already mentioned over there also, histogram equalization, principal component analysis, and tussle cave transformation. Although these operations has been in the next level, we will see in the advanced analysis and its applications. So far, this was all about the data corrections and some of the examples of the basic analysis or basic tools for the further analysis or preparing the data for the machine learning classification analysis. For now, thank you. See you in the next lecture.